and welcome to Biological and Physical Chemistry again. My name is Stephanie Schweiker and we'll be talking today about the second lecture, which is Aldehydes, Ketones and Carbohydrates. So what we're going to be talking about today is our nomenclature and an introduction about what aldehydes and ketones are. We're going to talk about how to prepare, so how to make aldehydes and ketones. Then we're going to be talking about the specific reactions that they undergo. So formation of alcohols, a reaction which uses a nucleophile. We're going to talk about Grignard reactions, addition of nitrogen and oxygen nucleophiles in the formation of amines, acetals, hemiacetals. We're going to look at reduction, and then we're going to go into a bit of biochemistry and carbohydrates. So aldehydes and ketones. So firstly, let's have a look at the structure of aldehydes and ketones. So aldehydes and ketones have the carbonyl group. So the carbonyl group is a positive carbon that's double bonded to an oxygen, which is a delta negative. So we've got a delta positive on the carbon and a delta negative on the oxygen. And this is a very reactive part of a molecule. So this carbonyl is quite susceptible to nucleophilic attack because it's a delta positive and the nucleophiles will seek a positive charge. Okay, so it's quite a small bond, this carbonyl bond, double bond, that's between the carbon and the oxygen. So there's lots of functional groups that contain this carbonyl. So there's your aldehyde, your ketones, your carboxylic acids, and your esters. There are a couple of examples of that one. So the carbon is sp2 hybridized and therefore has a planar shape. Okay, and like we said, because of this electronegativity difference along the carbonyl bond, it's very susceptible to attack by nucleophiles. So firstly, let's look at an aldehyde. So when we're doing the naming of an aldehyde, we remove the E from the parent name. So if it's an alkane, we remove the E and we add Al. So it'll be an alkanal would be the general name for that one. And an aldehyde is a terminal group. So it's when you have a carbonyl that has a hydrogen on one side and an R group on another side. So terminal means it's always going to be at the end of the chain. Because it's going to have 3 bonds taken up by that functional group, it's always going to have to be located at the beginning or the ending of a chain. So our simplest one is eth alkane with an aldehyde, so to be ethanal. And then we've got propanol, if we go up an extra carbon. We've got butanol, introducing another one, and then we have pentanol when we have 1, 2, 3, 4, 5 carbon aldehyde. Now, because the aldehyde's at the terminal position in all of these ones, you don't need to indicate that it's number 1, it's implied again. So looking at our looking at another structure for an aldehyde, we've got benzaldehyde. So this is when we have a benzene ring, so an aromatic benzene ring that has an aldehyde group coming off it. So benzaldehyde. So our other ones are ketones. So ketones are similar. They've got this carbonyl region in the molecule, but this time they have an R group coming off both sides. So there's no hydrogen, there's 2 carbons. With the nomenclature, again, if we were to have an alkane, we would remove the E and add O-N-E. So it'll be an alkanone. So the carbonyl, which is the ketone functional group, can be located anywhere within the chain. It doesn't need to be at the end or the beginning of the chain, it can be anywhere because it's got 2 R groups that come off it and 2 bonds used in the carbonyl. So they're less reactive than aldehydes and are often used as solvents. So an example of a ketone that's a solvent is acetone, and quite commonly you'll find acetone in nail polish remover, unless you get the acetone-free nail polish remover, which has your ethyl acetate as a replacement. Okay, so let's have a look at some more examples. So we've got our methethpropanone, which is our acetone. We've got methethprobutanone. We've got methethprobutentanone, and we've got methethprobutentanone again. Okay, so if we look at these ones, because it's on the second one, it hasn't been written in, because it has to be off the second one if it's going to be the lowest number. So you can see with the bottom two here, so this one again, second one didn't write in, so they could have wrote 2-butanone or butanone, it's implied. So here they've actually specified that it's 2-pentanone, and here we have 3-pentanone. So it's 1, 2, third carbon's got your ketone, and 1, 2 has got your ketone here. So aldehydes and ketones can be produced via oxidation of primary or secondary alcohols using strong oxidizing agents such as potassium permanganate or potassium dichromate in acid. Okay, and we'll talk about these ones a little bit later on. So some more examples about natural aldehydes and ketones in natural compounds. And aldehydes have quite pungent smells, and others can have very pleasant odours. So example here is cinnamaldehyde, which is cinnamon. Okay, so as we all know, cinnamon's quite pleasant. We've got camphor, which is your ketone. We've got progesterone, which is your ketone again. Here we have vanillin, which is a nice vanilla smell. We use it as a stain for TLC plates in our lab. And here we have an aldehyde functional group there. We've got a benzaldehyde. Citronella is an aldehyde, and testosterone is a ketone. So there's some examples there of natural aldehydes and ketones. Okay, so let's have a go at a practice question. So this one is classify these as aldehydes, ketones, or neither aldehydes nor ketones. So firstly, butanal. So the Al is indicating that it's an aldehyde group, and butan is methethprobut, so it's a 4-carbon chain with an aldehyde on the terminal side. The next one is an aldehyde. We've got our carbonyl with a hydrogen and a CH3. And the third one along, we have a ketone, so a carbonyl in between 2 carbon chains. The next one we have is methylpropanoate, so it's got an O8 ending on it, so a ketone has ONE and an aldehyde has AL, so it's neither an aldehyde nor a ketone, it's actually an ester. So methylpropanoate is an ester. Next one along is our CH3CH2OH, which is an alcohol, which we learnt about last week. And the next one here is a CH3CH2O, CH2CH3. So counting up our bonds off this carbon here, we've got 1 methyl, 2 hydrogens and an oxygen, and here we've got an oxygen, 2 hydrogens and a methyl, so it's actually an ether that we've got here. And again we've got an O8 again, so we've got another ester. An al is an aldehyde. Butanone is a ketone. This one we've got a CH3CH2 carbonyl CH3, so a ketone. We've got a heptanone ketone. Propanoic acid. Oic acid is a carboxylic acid. Al is an aldehyde. Here we've got an alcohol, so single bond to an oxygen, single bond to a hydrogen. And here we've got a benzene ring with an aldehyde coming off it, so a carbonyl with a hydrogen. Okay, so let's have a look at our key concept reactions. So we're looking at oxidation, reduction, and nucleophilic addition. So ozonolysis is one way of preparing aldehydes and ketones. So it's when an alkene reacts with ozone, followed by a mild reduction using dimethyl sulfide. Okay, so it's a two-step reaction, and this is indicated by 1, 2. So the first thing is reaction with ozone, and then the next one is the dimethyl sulfide. And this is our starting generic alkene, and we've got a split down the middle, and an oxygen goes on one side and an oxygen goes on the other side. So we've got a ketone on this side because there's 2 R groups, and we've made an aldehyde with the other side because we started with 1 R group and 1 hydrogen, so that would give us an aldehyde. Okay, and we've got our byproduct. Oxidation of alcohols. So the main way aldehydes and ketones are synthesized is from oxidation of the corresponding alcohol. Okay, so if we start off with some kind of alcohol, so let's have a look at a primary alcohol. So remember, a primary alcohol has 1 R group and 2 hydrogens attached to the alcohol moiety. If we oxidize this using 1 equivalent of oxidizing agent, we would go to the next step, which would be our aldehyde. So a carbon double bonded to our oxygen with a hydrogen attached and an R group attached. And if we oxidize it again, we would actually move up to a carboxylic acid. So the second oxygen would add on here to the hydrogen spot on the central carbon, so we get an alcohol, so an OH, and the alcohol and the carbonyl going together makes a carboxylic acid. So what we can say here is primary alcohols can be oxidized to the corresponding carboxylic acids using strong oxidizing agents. So our 2 strong oxidizing agents are potassium permanganate and potassium dichromate, or potassium chromate. So if we don't want to go from an aldehyde to a carboxylic acid, we need to make sure that we've got the right equivalents of oxidizing agent in there, and that can be very, very difficult. So usually what you do is you choose a milder oxidizing agent, so that way you don't accidentally go the 2 steps, you just do the 1 step. So an example of a milder oxidizing agent is your pyridium chlorochromate, so your PCC, pyridium chlorochromate, and it's quite commonly used because you can just put it in, leave it, you know it's going to go to the aldehyde, you're not going to push it all the way to the carboxylic acid, and it's soluble in organic solvents. Okay, so it's quite popular. So normally the other oxidizing agents are done in an aqueous environment. Okay, so secondary alcohols are oxidized by pyridium chlorochromate, so PCC, or potassium dichromate to the corresponding ketone. Okay, so you can use a mild or a strong oxidizing agent when you have the secondary alcohols, because the most that it can do is go to a ketone. It can't go to a carboxylic acid. So looking here, we've got our secondary, so 1, 2 R groups, there's the hydrogen that's not drawn in, and we've got the alcohol. And if we oxidize that as much as we possibly can, we're only going to be making a double bond to that oxygen and making the ketone. We cannot go further to form a carboxylic acid. So it doesn't really matter what oxidizing agent you use for secondary. For primary, you need to make sure that you choose the right one. So tertiary alcohols resist oxidation as the carbon-carbon bond would need to break. Okay, so if you've got 1, 2 and then another R group, you won't be able to oxidize that because you've got 3 R groups attached, and there's not enough room to make that extra bond going to it. So it's only primary and secondary alcohols that oxidize. Okay, and so here's the reaction that goes there. So we've got our pentan 1-ol, so our primary alcohol with pyridium chlorochromate, and that will make our pentan al. So this is this statement here. Okay, So no matter how much you put in there, you will not get that PCC reaction with a primary alcohol go further than an aldehyde. So let's look at reduction. So reduction is the opposite to oxidation. So oxidation, we're adding in oxygens, removing hydrogens. Reduction, we're removing oxygens and adding in hydrogens. So aldehydes and ketones are easily reduced back to their corresponding primary or secondary alcohols. So how can this be done? So we can do this with some sort of metal catalyst and hydrogen gas. Okay, so hydrogenation we talked about last lecture was H2 and palladium, so PD as the catalyst. When we do that, we reduce the ketone. We reduce the ketone to the alcohol, and we also reduce any double bonds or triple bonds that are in that molecule. So if we have a carbonyl and an alkene, we would reduce that down to an alkane and an alcohol if we used hydrogenation with a metal catalyst and hydrogen gas. If we use a metal hydride, we not only maintain our alkene, so our alkene is not changed. So if we use a metal hydride, our alkene is not changed, it stays there, and only the ketone is reduced down to the alcohol. So your metal hydride is a metal attached to a hydrogen, and because of the dipole moment across that, it's basically equal to a H- floating around. So the reactivity is basically equal to that. So what we know is that our metal hydrides will reduce our carbonyl to our alcohol, but it won't touch any alkenes or alkynes that are in the molecule. The metal hydrides are a source of H-, which is a very, very strong nucleophile. Our hydrogenation reactions with a metal catalyst and H2 will reduce our alkenes or alkynes down to alkanes, and it will reduce our ketones down to our alcohols. Okay, and so let's have a look at the nucleophilic addition reactions of carbonyls. So again, nucleophiles is represented by the NU with 2 dots on it, representing the lone pair that's on the nucleophile. So looking at our carbonyl, we have our carbon double bonded to our oxygen, so our delta positive and delta minus. We have the negatively charged nucleophile, or the lone pair from the nucleophile, attack the positive, and then the electrons from the double bond kick onto the oxygen. Okay, so then we have this extra bond to the nucleophile. We have the negative charge now on the oxygen. So now 2 things can happen. Depending on your reaction, you can have that negative charge kick back down and kick something out, or that negative charge needs to be quenched. So with these types of reactions that we're looking at here, we've got that lone pair, that extra lone pair of electrons now, that negative charge being protonated from the aqueous environment that the reaction is done in, or from the acid source that's in this reaction, and it's forming your alcohol. Okay? So we've got our nucleophile attacking our carbon, we've got the lone pair of electrons, so the bonding electrons moving up to becoming a lone pair of electrons. Then we've got a negative charge. That negative charge is quenched by the addition of a proton and forms the alcohol. So you'll be looking at this mechanism again in Biochem 1 or Medicinal Biochem 1, and you'll be looking at enzyme catalyzed mechanisms of proteases. And it will just be the same thing as you see here. Now let's look at aldehydes and ketones and their reactivity. So the main thing that we haven't talked about from last time is the Grignard reagents. So we talked about alkyl halides, but we didn't talk about the Grignard reagents, so formation of the Grignard reagents. But we did talk about SN2, SN1, E2 and E1. So first of all, we're going to just finish off this section here by talking about the formation of the Grignard reagents. So Grignard reagents are reagents that are used in the Grignard reaction. So they're formed by reacting magnesium and a variety of starting materials. So what we have here is we have an R group. So it can be primary, secondary, tertiary, an alkyl or an aryl. So it can be primary, secondary, tertiary, an alkyl or an aryl. So an aromatic. So an alkenyl is an alkene that's a substituent, and an aryl is an aromatic group that's a substituent. The X can be a chlorine, bromine or iodine, and these reactions typically occur in ether or THF. And what we've got forming is we've got our R group, our magnesium, and then our halogen. So for example, we've got one bromobutane. Okay, so we've got a bromo, we've got our butane here, so we've got our delta positive, our delta negative, we've got magnesium. Okay, so that's one of our reagents, and it's done in THF, which is the solvent. So the THF isn't doing anything, it's just the medium in which the reaction can occur. So the magnesium squeezes in between the alkane chain and the bromine, and we get our CH2 MgBr in the terminal end. So it's now called butyl magnesium bromide. So magnesium bromide is the parent name of this molecule, and the butyl is the substituent that's coming off it. And generally, the nomenclature of this reagent here is called alkyl magnesium halide. Okay, so we say the alkyl group, the magnesium, and then the halide that we have. Okay, so have a look at the key thing in this reaction here is we've now got the CH2, which is a delta positive at the start, has become a CH2 that's a delta negative because of this magnesium that's now in there. Okay. So let's have a look at the reaction. So now that we've made our reagent, let's have a look at the reactions that aldehydes and ketones do. So the nucleophilic addition reactions, we've talked about the mechanism of this. We're going to now see Grignard reactions, imine, acetals and hemiacetal formations, and alcohol formation. So let's have a look at the Grignard reaction. So many carbon metal bonds are covalent, but when the metal is quite electropositive, such as the magnesium in magnesium bromide that we've got here, so it's delta positive, the bond is more polar and the electrons reside closer to the carbon. So basically, because of the polarity difference between the magnesium and the carbon, this carbon here acts as a C-. Okay, so we've got this carbanion group that's formed. So the C- can then act as a nucleophile and attack the carbonyl carbon. Okay, so it's a very strong nucleophile. We have nucleophilic attack. Okay, so it attacks the carbonyl carbon. We have the electrons kicking on to the oxygen, forming a negative charge. We've got our new carbon-carbon bond that's been formed. And this is called an alkoxide. So we talked about alkoxides last week. Okay, and then again, that one will pick up a proton from H3O molecule and make H2O, and this becomes an alcohol group. So they're actually quite difficult reactions to get good yields on. I have done them quite a few times in the past, unfortunately on very large scales, which wasn't too pleasant. So the Grignard reagent that you're making is a very strong base, that carbanion, and they're moisture sensitive and are usually prepared fresh on the spot with absolutely no water in sight. If there is water, the magnesium bromide is cleaved and the reaction won't work. Okay, so in the cleaving process, you would just end up with the propane. Okay, so you've got to make sure these reactions are super, super, super dry, and you make them and use them in an argon atmosphere normally. Okay, so when you do a Grignard reagent, you start with your carbanion. Okay, so your carbon that's an anion, and you have a ketone, and that's what's reacting. So depending on the ketone that you use, you'll get a different product. The Grignard reagents are very versatile in the fact that you can start with a different range of reagents and end up with ketones or alcohols. So, for example, if you have a nitrile as the carbonyl, a CN instead of a CO, you can still end up with a ketone. If you have an acid chloride, you can still end up with a ketone. So there's a lot of variety in the starting reagents that you can use. So we're going to go through 3 examples of how you get to the different alcohols. So you can get to a primary, a secondary, or a tertiary alcohol, and it's dependent on the carbonyl that you choose to go with your carbanion. So if you choose a formaldehyde, which is a carbonyl with 2 hydrogens coming off it, and you have your carbanion come and attack your delta positive carbon, you'll get the electrons kicking up onto your oxygen, getting that negative charge, which is then quenched into forming that alcohol. Okay, so this becomes a CH2OH, and you have your 3 carbons, so CH2OH and your 3 carbons. So this one is a primary alcohol. Okay, so the carbon with 1 R, 1 OH and 2 hydrogens that you have formed. If you then use a carbonyl that has 1 R group off it, okay, so an aldehyde and your carbanion, you will get a R group coming off like before, and you'll get another R group coming off, so you actually make a secondary alcohol. If you use a carbanion reacting with a carbonyl that has 2 R groups, so a ketone, you will get a tertiary alcohol being formed. So the mechanism is the same, but depending on how many R groups you have coming off that carbonyl will depend on the type of alcohol that you're forming. So we can get a similar sort of thing happening with different nucleophiles that are nitrogens and oxygens instead of carbanions. So when you have a nitrogen or oxygen nucleophile, you form imines, acetals and hemiacetals. So imines are carbons that have a double bonded nitrogen to it. Acetals are carbons that have an OR group attached to it, so 2 OR groups attached to it. And a hemiacetal is an OR group and an OH group attached to that carbon. So the formation of the Grignard reaction, so the carbon-carbon bonds, proceeds in the forward direction, not under equilibrium, but the other nucleophiles that react with the carbonyl compounds are under equilibrium conditions, and you'll see that in the next slide with the mechanism. So the 2 most important are your carbonyls reacting with your amines to make your imines, okay, which are weak bases. Your amines are weak bases, and your carbonyls with your alcohols making acetals and hemiacetals depending on how far that reaction proceeds. And we'll look at the biological significance of these types of compounds a little bit later in the lecture. So imines are known as shift bases. Okay, So they're characterized by that carbon-nitrogen double bond, and they're formed by acid-catalyzed condensation of a primary amine. So remember, an amine is an NH2 group that is attached to a carbon chain. So we've got propanamine, so we've got our amine and we've got our propan group there, with propanone, so a ketone, and under acidic conditions at equilibria, you can have this nucleophilic attack. Okay, so here's the mechanism here, the nucleophilic attack of the carbonyl carbon, and then you'll have the formation of your imine. Okay, and under equilibrium, if you remove the excess water, you can drive it across to that imine formation. So let's have a little bit more of a look at this mechanism. So we have the formation of the nitrogen-carbon bond. By doing that, we're introducing an extra set of electrons to that nitrogen, so we pick up a positive charge. Okay, so there's too many bonds going to that nitrogen now, so it's got a positive charge. So we need to deprotonate, so remove a proton from the nitrogen. And because we've had the kick up of those electrons onto the carbonyl oxygen, we then have not enough bonds going to that oxygen, so we have a negative charge. So basically we've got to do a proton transfer from the nitrogen to the oxygen, and this can proceed via something that's close by. It could be water, or it could be simply the oxygen picking up the proton. Okay, so we have that proton being removed and a proton adding onto the oxygen, so now we have an alcohol, and we have the carbon nitrogen, so an amine. We then have another proton added to the oxygen, so this is the tetrahedral intermediate. We have another hydrogen added to that oxygen, and we make a water molecule that's still attached. Okay, so this one can leave very easily. We've talked about it in the past. It's a great leaving group. It's positively charged. It wants to get rid of that positive charge. It's in an aqueous environment or acidic environment, so it can just come off. You then have the deprotonation of that extra hydrogen on the nitrogen, and the nitrogen forms the double bond to the carbon, and you make your imine. So hemiacetals and acetals are formed by reactions with alcohols and aldehydes and ketones, again in the presence of an acid catalyst under equilibrium conditions. So the aldehyde is the minor product and is less stable. Further reaction will give you that acetal product and some water. So acetals are stable under basic and nucleophilic conditions, but they are not stable under acidic conditions. So when they're under basic or nucleophilic conditions, it's a way of protecting an aldehyde or a ketone. So they're used as protecting groups. The way you remove your protecting group is by putting it under acidic conditions, and then you will regain your aldehyde or your ketone that you had initially. Okay, so it's under equilibrium and it's reversible. If it's under an acidic condition, you can remove these groups and go backwards. So the reaction is at equilibrium. The hemiacetal group is your carbon with an OR and an OH, and your acetal is with two ORs, so two ethers. So remember we talked about ethers last week. So let's have a look at the mechanism of the acetal formation. So a two-step mechanism that proceeds by that carbonyl, so the same as the amine does. So firstly we have the acid-catalyzed attack of the carbonyl, and we've got the formation of the oxonium ion, and then we've got further loss of water, which leads to the carbocation. That's your intermediate. So we've got our hemiacetal here. So we've already done one side, and we're just going to have a look at doing the other side now. So now this alcohol here and the ether on this side. So we've got the lone pair of electrons kicking down and we've got the protonation of this alcohol to form the oxonium ion, which is then liberated, and we have a double bond to our once OR group, so it's now an OR plus group because it's got that extra bond going, and then we have the positive being stabilized by moving on to the carbon, okay, because now we've lost that group, so we've got the carbocation intermediate here, and then another alcohol molecule will come along and add on, and we'll get the deprotonation, and we'll get those two ORs that are attached. Okay, so hemiacetals are important in carbohydrates, which again we'll talk about soon, and they gain stability by undergoing intramolecular hemiacetal formation. This is when they have both groups in the same molecule spaced apart, so that you can have that cyclization within the molecule. Okay, so just remember your reduction reactions like we talked about before. So it's exactly the same slide as before, so this is just me refreshing you on what we talked about. So we've talked about hydrogenation in the past, where you've got hydrogen and a metal catalyst such as palladium. Under these conditions, you can go from a carbonyl to an alcohol, but you also lose any double or triple bonds that were on the original molecule, going down to that alkane. If you have a carbonyl and a double bond and you want to retain that double bond, you need to use a metal hydride. Okay, so metal hydride such as sodium borohydride, sodium triacetoxyborohydride is another example that's less harsh compared to sodium borohydride, and we keep that double bond there. So what is the mechanism for this one? Okay, so the reduction mechanism with a strong base, we have our H- that's produced. So this is what sodium borohydride looks like. We've got this B-, which acts as a H-, so it's producing that H-, and we've got the carbonyl carbon being attacked, and we've got that O- being formed, which is then protonated to make the OH, and we've got that H that's left on there. So lithium aluminium hydride and sodium borohydride are the two examples that you need to remember for this course. Okay, so depending on what you want, you would choose one over the other. So sodium borohydride is mild in comparison to lithium aluminium hydride. It's selective for aldehydes and ketones only. Lithium aluminium hydride is a more powerful reductant, and it reduces aldehydes, ketones, as well as carboxylic acids and esters. Okay, so it pretty much reduces anything that it comes in contact with, whereas sodium borohydride does not. So let's have a look at tautomerization. So this is when we talk about keto and enols. So a ketone is when you have your carbonyl carbon and your alpha carbon, so the carbon next to it, having a single bond, and your carbonyl being there. And an enol is when you have the double bond next to your carbons, so between your alpha carbon and your carbonyl carbon, and your carbonyl is now an OH group. So the enol comes from this OH, and the keto comes from the ketone that's there. So we've got our keto-enol form, and this can be of a ketone or an aldehyde. So this is your ketone, and an aldehyde would just be an H instead of this R group that's there. Okay, so it's the process where two isomers, an aldehyde ketone with its pair, either in the enol form, are interconverted by a formal movement of an atom or group. Okay, so aldehydes and ketones pairing the alpha hydrogen, which is a hydrogen that is a carbon next to the carbonyl carbon, are able to undergo tautomerization to form the enols. So what we're saying is that you really need this carbon with a hydrogen here so you can make that double bond there. So it's a nice easy group that can be removed easily. Okay, so they're structural isomers with respect to one another. So this is a very acidic proton, and this is exploited in this process. Okay, so your keto form looks like this. So you got that ketone group, you get that attack of the acid proton that's close by, and you get the OH being formed with the double bond. To get rid of that double bond, we need to add an extra bond to this carbon here, and that is done by an acid catalyzed proton removal. So that is done by your water molecule coming and removing that acidic proton and getting the double bond being formed there, and then you have that OH that's now neutral, and that's your enol. And so this happens quite fast, but this step here is fairly slow. So for example, the position of this equilibrium, for example, depends on the compound that you have. So for acetone, it's 99.9% in the keto form and 0.1% in the enol form. And every compound will have a different characteristic on how they sit between keto and enol. So let's have a look at some examples. So let's have a look at our alcohols and their oxidation. So if we had potassium dichromate and we had an alcohol, what product would we form under acidic conditions? Okay, then if we have that product and we react it with a Grignard reagent, so CH3 MgBr under acidic conditions, what would we form? And then if we had that compound and had it under acidic conditions, what would happen? Okay, so the first one that you will get would be this compound here. So let me just, okay, so we've got an alcohol, it's under harsh oxidizing conditions. It's a secondary alcohol, so the furthest that you can push a secondary alcohol is into the ketone. Okay, you then have that ketone available, that carbonyl carbon, to be attacked by your Grignard reagent. So your CH3 minus is going to come in, attack that carbonyl carbon, and you will get a methyl group added, and your carbonyl will turn into an alcohol. Okay, and then under acidic conditions, you would get an elimination reaction of that OH, so a dehydration reaction, so the OH and the H would be removed. Okay, and you would get that double bond formed. So that's going back to last week's lecture. So another one is if you have a primary alcohol and you have pyridium chlorochromate, so PCC, you would form your aldehyde, your PCC. And if you have a primary alcohol and you have a chromate oxidizing agent, what would happen? So your PCC, you would go that one step to your aldehyde, and your harsh one, carboxylic acid. You'd go all the way to a carboxylic acid.